Okay. Hi, everyone. I'm Philip. Let's see where we can take this. I work for Elastic, as you might have guessed, and I want to talk a bit about data stores and their trade-offs and how to kind of make them fabulous. You will get the fabulous pun in there as we go along. So first things first, my role is I'm a developer advocate. So at Elastic, I mostly speak about the good stuff that we do, or try to get your feedback and see what is working or not working for you. I always use the avocado because everybody is confused, like, what does this mean, like a developer avocado? But my job is mostly to just show you what cool stuff you can do. So most of you are probably familiar with our stack. So here you can see this is what we have, and probably you've used quite a few of those components since you're in this webinar. Today we just will focus on Elasticsearch itself, so only the data stores side. So now, knowing where I work and that we have this stack, what is the perfect data store solution? And if you say Elasticsearch, I would not necessarily totally disagree, but I would slightly disagree, because the perfect data store solution, as always, is it depends. And that is very much the topic of this talk, that I want to show trade-offs and that there is no one best solution, but you have to pick the right trade-offs. And in many situations, Elasticsearch will be the best choice, but not necessarily for everything. You need to pick the right trade-offs. And this is where what we want to dive into. Also, you might have heard that it depends from a consultant. Normally, that's when they start charging you a lot of money for afterwards. We won't charge you money here. The only thing that you need to keep in mind is every time you say it depends, you need to kind of define on what does it depend on. It's not just an excuse to get out of a question. It's more like to say, like, these are the trade-offs that we want to cover here. And let's see some of the trade-offs that we can have. So the entire goal here is to pick the right trade-offs. Sometimes people promise you something like magic, like this. There is no magic tool. Like, it's all about the trade-offs in the end, and that's where we want to head. So who knows the FAB theorem? The consistency, availability, and partition tolerance is the basis of that. So if you've never heard of the FAB theorem, we'll take a quick recap. There is this paper here from Seth Gilbert and Nancy Lynch, and it was actually based on a talk by Eric Brewer, working for Google. And he had this idea that you have these three attributes: consistent, available, and partition tolerant web services. So it doesn't only apply to web services, but to any kind of distributed system. And his main idea is that you want to have all three, but you can have at most two of these attributes. By the way, it's not guaranteed that you have two. Like, if you build a bad system, you might only have one or zero of these attributes. So it's not guaranteed that you get 2 out of 3, but at most you can have 2 out of those 3. So let's take a quick look at what are these 3 things that you might want to have. The first one is consistency. You basically have a total order of all operations. Imagine you have a distributed system, but it still looks as if you had one order of all the requests going through your system. So it's as if you had a single lane and every car or request had to pass through that single lane in one total order. So at one point in time, you always know what is the current state and where are you. So it is as if you had a single instant, even though you have a distributed system behind it. Then you have availability. Availability basically means that every request that is received by a node needs to be answered. And the node cannot just decide, no, I'm not sure in what state I am right now, I'm not answering. It has to answer to have this availability attribute. And finally, partition tolerance. Partition tolerance is an attribute that you pretty much have in any distributed system, that the network will lose messages, or that you're not sure, is a node down, or is it just in a long garbage collection? For some reason, something is not working quite the way it is expected to be. And messages can be lost, nodes can crash, etc. And that is pretty much a precondition in any distributed system. What you get out of these is that you end up in this diagram, and you can see you can only pick 2 of these 3 attributes, but there is no middle which has all 3 basically. So depending on what kind of system you have, if you have like a relational database, you're more in the consistency and availability area. because the distribution and thus the network partition is kind of harder or more complicated to do in those systems, if at all. And thus, you can only pick 2 of the 3 attributes to build a system that conforms to those. And if you want to have a better understanding of that, you need to be aware of 2 misconceptions that you could run into. First one is that sometimes people claim a partition tolerance is something you could just not have, which is not really true. Like, you have them unless your monitoring is bad enough, and then you don't see them maybe, but they are probably there. Like, there is a very nice paper, for example, how many network partitions or trouble Amazon, Microsoft, or Google have in their data centers. So as soon as you have a large enough distributed system, you will have some partition tolerance, or you need to sustain some of that in your system. And if you don't pick that explicitly, random stuff will happen, so you don't want to have that happening. The other thing is that consistency is unfortunately an overloaded term. There is consistency in ACID, the transactionality of requests, where it is a predicate. A predicate basically means that you move from one correct state to another. So for example, you have a not null constraint, you have a referential key integrity. That would be the consistency that the data is in a consistent or correct state. And that is the consistency in ACID. Whereas in CAP, it's a linear or temporal attribute that at one point in time, you have one single view of the entire system that you have. So in CAP, it's a different consistency, unfortunately. Don't be confused by that. If you want to explain the concept to your kids or maybe to your parents, you could use Robinson Crusoe, because Robinson Crusoe is basically partitioned from the rest of the world on his lone island. And I think he was British. So let's assume a ship comes by and asks him, who is the king or queen of England right now? And then Robinson Crusoe basically has to decide, am I consistent or am I available? Because if he answers, then he is available, but he might not be consistent with the rest of the world. Or if he doesn't answer, he's not available, but he is consistent with the rest of the world because he doesn't give a wrong answer. And that's also the entire idea of the paper. And it's not very math heavy or anything, it's rather constructive. And the idea, for example, is that you have 3 nodes, and then the network breaks in the middle. So you have 2 nodes on one side and 1 node on the other side. So you have the network partition. And then you write some new messages to these 2 nodes here. And at the same time, you might start querying this other node. And then this node here basically has to decide, am I consistent or am I available? Because if it doesn't answer, it's not available because, well, it's reachable, but it decides not to answer. Or it is figuring out, well, I don't see anything from the rest of the world, so I cannot answer. Then it is, if it's not answering, then it's consistent because it's not giving a wrong information, but it is not available. So the node basically has to decide which trade-off do I pick. And there is no good way around that. By the way, does anybody recognize the island? It's from a movie in the last couple of years. Sometimes people know or guess it correctly. It is from Star Wars because all the examples that we'll cover will be from Star Wars as well. But this is just preparing for you. And finally, one other thing, you can break the CAP theorem, but you might not get a useful system out of that. So for example, def null is kind of breaking CAP because it always gives you the answer, the same answer, nothing. And it's always available, but it's not really the kind of system that you want to have. So this is not useful or helpful in any way. Okay, enough of the CAP theorem. Let's move on to the FAB theory. This one doesn't have a fancy paper. This is just a theory that one of our colleagues at Elastic came up. This is the colleague, Mark, showing him at his favorite hobby. And he had the kind of same idea that there are 3 attributes that you want to have, but you can only have 2 at the same time. So the idea is very similar, but let's dive into the attributes that you have. Fast is the first one. So the attributes are fast, accurate, big. Fast is you have something that is answering in near real time. So basically, you run a query and the human waits for the answer. So it might take 1 or 2 seconds. It's not like a batch job that might run overnight or 15 minutes or whatever when people go for a coffee. Fast is you want to wait for the answer. So that's an attribute that you generally want to have, I can get it pretty much right away, the answer. Next up, accurate. Accurate is pretty intuitive. You get the right answer. And that one is a bit more confusing, and we'll return to it later on, because accuracy, how would I use an inaccurate or wrong answer? Maybe wrong is too strong, but then not 100% exact answer. And we'll see how that could be useful and what are the trade-offs in that one. And finally, big. Big is any workload that you need to parallelize to actually run. And I'm not a big fan of that term big data, because by now it's mostly marketing and nobody really knows what it means anymore. But we'll just stick to the very simple definition of you can parallelize a workload, or you need to have a parallelized workload to actually be able to run it. So basically anything you cannot run on your laptop. So my demo will be on my laptop, but the principle will be something, or will build on something that you would be able to parallelize. So skipping over big data, because I think this is the thing that we always think about when we hear big data. Avoid the term because it doesn't mean anything. Let's dive into the actual details. So fast is probably clear, like you wait for the answer. Big, you need to scale it horizontally over multiple nodes, is probably also clear. Accurate is a bit more confusing. How could something be inaccurate and still be useful? So let's see how Elasticsearch handles this. And this, by the way, does not only apply to Elasticsearch. This applies to many other systems, but obviously we will use Elasticsearch as our system to use that. The only thing that you need to know about Elasticsearch, by the way, is how do we scale Elasticsearch horizontally? We have shards. So we have an index, kind of related data put together, and then we can break that up into multiple smaller pieces. And those can be distributed over multiple nodes. So that's the way how to horizontally scale data out. And that's pretty much all the concepts that you need to have. By the way, since we're already doing Star Wars and other fun stuff, do you know where the term shard is coming from? And maybe this is not entirely true, but this is the story I believe in. Does anybody remember this one? Maybe you're old enough to have played that game a while ago. You can see from the graphics, it's not the most current one. This was Ultima Online. And the story there is, there was a wizard and the world was trapped in a crystal, and then the crystal was broken up, and the different pieces of the crystal held, or pieces or shards of that crystal held a part of the world that you could play. And according to this story here, which is already quite old, this is where the term shard is coming from. And it's pretty widely used over multiple distributed systems. Like every time you break up data, it's called a shard. So this is the story I believe in. Maybe it's not 100% correct, but this is just on the trivia side of where shard might be coming from. Okay, let's start with term segregation. What was a term segregation again? The term segregation is the top n results. So what are the most common terms, basically? So here, as I've said, we would use Star Wars. I'm using Star Wars. And this is the very first movie that came out. So I think by now it's called Star Wars 4, but naming is confusing there. So the very first movie. And somebody luckily counted the most common terms you have in Star Wars. So you can see Luke appeared 64 times and R2 31 times, etc. So this is how many times all of these terms appeared. And we'll stick to the top 16 terms. So we're not indexing more. What I'm doing now is I create an index with 5 primary shards. We don't need replicas today. We just need 5 primary shards, so we can scale that horizontally. And then I use a bulk request to actually store these documents. And as you probably know, the first line is always basically the metadata, or where to put the data. So here you can see, put this into an index Star Wars. And then we have some routing information. We'll get back to the routing information in a bit. The actual document is always the even line. So here you can see we have one attribute word and it has Luke, and we have 64 of these documents. And then we will have 31 documents with R2. And that is the data that we store. And this is something that you could build out of that tag cloud. Just to give you a quick idea, I have already inserted my data. I have not created the index pattern. So let's quickly create the index pattern, just so that you see that part, because that's what is still confusing a lot of people. You always need to create the index pattern. So we'll go for Star Wars. It doesn't have any timestamp or anything, so we'll just create that. And then we can actually build the tag cloud out of that. So we go to the visualizations, create a new one, and then the one we want is a tag cloud here. We pick the Star Wars index. Right now, we have one big aggregation of all the data, and then we break this up into different tags. And the one that I want is terms. And in here, we have the word that we want to aggregate on. Let's say we want to have the top 20 terms. When I run that, you can see, okay, this is the aggregation that we get out of this. The one question to keep in the back of your head now is it very relevant if those results are exactly correct? Does it make a difference if we have 60 or 64 loops? We'll come back to that, because maybe it's not so necessary. It's rather important to get this result quickly and without wasting too many resources. So here you get an approximate idea of what you have, but if this is 100% correct or not is not really the point. So let me head over to my slides. What we want to have is, now we want to search actually for Luke. This is just a, I don't know, a regular search where we were searching for the term Luke. And actually, let me quickly cheat and get my data out here, because, no, this is the wrong one. Give me a second, sorry. I needed to copy some data here. This is the one. Make your data fabulous, and we need the actual queries that I want to run here. So let me cheat and get my queries. These are the ones that we will be running today. And let's hop over to console to actually run those. Okay, let's run this. So we have, you might have guessed it, we are running the latest version of Elasticsearch. And we have already inserted the data, and you can search for that. You can see this is one document that we have. Here you have the source. It's Luke, and we have 64 of those Lukes if we search for that. Now let's switch over to an aggregation. So we have an aggregation. I call it the most common term. What I want to get is, I want to get the most common term based on this word field. And I only want to have the top one, so the most common one. Don't be confused by that other size. You might have seen that. By default, you would get the first or 10 documents back from that aggregation. I'm setting that to 0 here because you don't want to get any of the actual documents from your aggregation. What you want to get is just the aggregation itself. So when I run that, how many Lukes are we expecting? 64 probably. So let's run that. And then you can see, okay, suddenly we only have 60 Lukes. This is very confusing. And to say it in Luke's own words, oops, go away. To say it in Luke's own words, that's not possible. Well, it is possible. Let's figure out why it's possible or what is happening in here. So I have kind of cheated a bit in here. So what we've done, or what I've done here, is I've prepared the data in a specific way that the Lukes are very unevenly distributed in the different charts. So the first 10 documents are evenly distributed. You can see 0, 1, 2, 3, etc., 8, 9. They always use different routing keys. And then all the 54 remaining Lukes use the same routing key. And then you need to remember, how does Elasticsearch distribute documents when you store them? You hash the routing key, then you count it modulo the number of primary shards, and that is the shard where this will end up in. So if you're using the same routing key 0 many times, this will always end up on the same shard. And the other shards will have very few Lukes. By the way, why do we hash the routing key? So that it's generally evenly distributed. So that is the general idea here. You want to have something that is evenly distributed. For example, if you had a string or an email address for the routing key, then you might have hotspots where E is a very common letter, for example, and then you might have lots of data points in there. So you want to have the key space evenly distributed to have an even distribution over your shards, which I have kind of circumvented by using exactly the same routing key all the time here. And what you end up in here is you can see the number of documents. You have different document or pretty different document counts here. And that is also because the loops mostly go to shards or have the routing key 0. R2, which is the second most common term, is then having the routing key 1. So it's like one specific keyword is always focused on one shard and has the majority of its data in one shard. And then there are very few occurrences of that term in the other shards. And this is why we are counting wrong here, because how you count that aggregation is that you don't get all the terms from every single shard, but you only get the number of results based on this formula. So size is how many results are you asking for? So I'm asking only for 1. 1 times 1.5 plus 10 is 11 or 12. It will be rounded down to 11. So every single shard, if you ask for the top 1 result, every single shard is only giving its own top 11 results. That is, of course, an optimization. Let's assume you have 1 million unique terms. Otherwise, you would need to generate, or every single shard would need to generate a list of 1 million terms and then hand that over to the coordinating node to combine those. And that would be quite a lot of overhead. So you would need a lot of memory to calculate it on every single shard. Then you have the network traffic to hand over 1 million results to a coordinating node. And then the coordinating node would have a lot of overhead just getting the top 11 results out. This here is based on the assumption that the data is more or less evenly distributed. Thus, if you just look for the top 1 result, it's probably in the top 11. And that would normally work out if you had an even distribution of data. Just in my data set, I've intentionally kind of circumvented that. So just to recap, we get 11 results per shard. Since we have 5 primary shards, we basically get 55 things to aggregate to get the top one element out of that. So this is what we get here. But as you can see, there is a doc count error upper bound and then other documents. So this is already in the query here. So here you can see upper bound is 10 and other documents. The other documents are basically all the non-Luke documents. The error bound, how could you calculate the error bound? The error bound is basically, you know, how many occurrences do you have in the 11th document? And then there could be something behind the 11th document. There are some occurrences that you're basically cutting off. And then if you add up the cutoff point of all the shards, you will get to that sum where these are the potentially missing counts that you have in here. Now, you can make this slightly more explicit and you add show term doc count error true, where you actually show the maximum error for one result. So here for Luke, it says there could be 4 more Lukes, which in our case is actually exactly the result that we are looking for. How does it calculate this one? It knows, for example, Luke is included in the top 11 results from this shard, so it's adding 0 error count. But in this other shard, Luke is not in the top 11 results. The 11th results had 1 or 2 occurrences, so that is then adding 1 or 2 to the potential error count that you could have. And this is already telling you how much you could be off in your result. So how could you circumvent that? What you have is you can add here something called shard size. And shard size basically tells each shard, don't take the top 11 or whatever the calculation comes out to results, but send at least or send 20 results per shard. And if you have this, since we only have 16 terms, Luke will always be included in the top 20 because there are only 16. And with that, you can see now we have an error count of 0. And now we're actually calculating correctly. And the total error bound is also 0 because, well, we included all the results, which for the small data set that we have, you can totally do. If you have 1 million unique terms, it's maybe something you want to be a bit more careful with because that will have a lot of overhead. But with this shard size, you can explicitly influence how much resources do you want to spend and how exact do you want your result to be. So this is what you can build here. Okay, so let's move on and take a look at another example, the cardinality aggregation. What was the cardinality aggregation? That was how many unique terms do you have in your data set. And let's assume you have more than 16, then that calculation could be rather expensive. What is the naive way to calculate this? Maybe something like this. You have a hash set or any other data structure that doesn't have duplicates. So you just throw in every single document into that data structure. It will overwrite the same ones. And at the end, you can just run size since you don't have duplicates, and that size will tell you how many unique terms do you have. The problem with this is, how does it behave in terms of performance, especially in terms of memory? This is rather unpredictable because this will just scale linearly with the number of unique terms. And it might just blow up your heap if it's a very large number of unique terms. And you probably don't want that. So you want to have a more clever way to calculate this. You're accepting that this might be slightly off, but you want to have a more clever way to actually do this. Let's take a step back and look at some different examples. Let's take a look at coin flips. What is the chance of having 3 heads in a row when you flip a coin? So for every single flip, it's 50%. If you have 3 in a row, it's kind of 1/2 times 1/2 times 1/2. So you multiply out those chances, because the more heads you have in a row, the less likely it is. So this is how you calculate those. Abstracting that is, if you have 3 coin flips, it's 1 divided by 2 to the power of the number of coin flips. So you have a chance of 1/8 for 3 coin flips. Or more generally, 1 divided by 2 to the power of k, and k is the number of heads you want to have in a row, for example. So this is how a coin flip works. Now, what you could do is you could apply that to our data set as well. What you basically do is you hash the value, then you have a binary representation of that, and then you count the leading zeros. Leading zeros in this example are read from the right to the left. So here you can see, if you just have these possible combinations, having 3 leading zeros would be a chance of 1 in 8 again. Or the general calculation applies, since with a binary representation, again, you have 2 options. It's 1 divided by 2 to the power of k that you could have. And this is what we want to build on. So rather than storing the actual values and then getting a size on top of that, we're basically only counting how many leading zeros have we seen at most. And based on that, we assume, okay, probably we have about that many unique values, which looks something like this green curve, because that is a bit wider and gives you potentially the wrong cardinality. So here you can see this point here, the true cardinality is this one. If you just have 1 hashing function, you would get a curve like that. Now what you could do is you could run multiple hashing functions and then average them out, called probabilistic averaging, because all of these data structures are probabilistic. If with multiple estimators, we could have this like more correct curve. Like it's still not 100%, but it's much closer to the actual value. The problem is, if you run multiple hash functions, those are potentially pretty expensive to run, because you will have, if you run 3, you will have 3 times as much CPU overhead at least, and 3 times as much memory usage, but the memory usage is very minimal because you only keep track of the maximum number of leading zeros. But you probably don't want to pay that price. So what you could do is you could do something more clever. And that's the log-log idea. So you're using a single hash function, but you're using it in multiple ways. So what this is doing is you're bucketing the hash values into different groups. So here, these are made up values, but for the idea, they illustrate that. So we hash Luke, and this is the binary representation of the hash that we get out of that. And then this part on the left-hand side, we use for the bucket. So we group our hash values into different groups or buckets. And then for the remainder, we just count the leading zeros from the right. So this here, the 0, 1, 0, 0, binary 4, that's bucket 4, and it has 3 leading zeros. Bucket 9 has 4 leading zeros. bucket 0 has one leading 0. What you basically do is you use a single hash function and you virtually group it into multiple buckets. So here, for example, I use 4 bits for the buckets, and then you just count the maximum number of leading zeros you have seen per bucket. And then you average those out. And that's the entire idea of log-log, that you average out those different buckets, and then you have a more exact calculation of the unique values out of that. And that's the general algorithm described in the paper. So this is just a pseudocode how to put that together. Then Google came along and improved the entire thing, called it HyperLogLog. And this is a bit of an improvement that keeps the error rate lower. And generally, the upper error bound is about 1% or so in the way they presented it. That is good enough for the approach they want to have here. So this is very fast. It's not 100% accurate, but it is pretty close, and it's much more efficient in terms of memory, and it's guaranteed not to blow up your heap. So you can run this query, and here I'm setting a precision threshold explicitly of 10, which basically means up to this value, you will have an exact result. For higher values, it will be an approximation and could be slightly off. Now, remember how many unique values did we have? 16. If I run that, the result will be, it tells me, okay, it has 17 unique values. So it's off by 1. It's pretty good for our small data set that, yeah, is maybe not surprising. And the optimization is a bit of an overkill for the number of unique terms we have. But imagine you have 1 million unique terms, then that optimization will make a lot more sense. So let's take a look at the parameters and how we can tune those. So the precision threshold is by default 3000. So up to that value, it will be exact. For higher values, it will be an approximation. You can then trade more memory use for more exact results. So you could set it up to 40,000. For higher values, it will always be an approximation. So even if you set a higher value, it would always be capped at 40,000, that precision threshold. Now, the nice thing about the precision threshold is that it translates directly into memory usage. So you take the precision threshold times 8 bytes. That is how much memory you will need for that calculation. So you know upfront how much memory will this calculation need. And there's no chance that you accidentally blow up the heap. And here, this is from our documentation. You can see an example like what is the approximate error count that you could have based on different thresholds. And you can see with a threshold of 10,000, the error rate, okay, here we have a slight spike to 1.5% or so, but otherwise it's way below 1% of the values. And as you can see, for lower values than the precision threshold, the result is exact. That's why the error rate only starts at higher values than the precision threshold. Okay. Now, if I would set that up to 12, and let's just run it live so you can see it, already when we set it to 12, this one is high enough that we get the actual result. And of course, if we set it to 16 or higher, it's guaranteed to be exact for our example. So this is how you can do the cardinality aggregation in a fixed amount of memory with getting pretty close results of what you want to have. Okay, should you pre-compute the hashes? So you could either do that client side, or there's the MapperMurmur 3 plugin that you could use on the Elasticsearch side. Should you always pre-compute hashes? What's the obvious answer? It depends. What are the trade-offs? So for large data sets and high cardinality fields, it might make sense. If you have a low cardinality field or a numeric field, then not, because numeric fields are very quick to compute on modern CPUs. So you probably waste more disk space than what you would be gaining in CPU. So that is what it depends on here. Okay, there were 2 potential improvements that we tried out. The first one was log-log beta. There was even a pull request. It turned out, or the goal of that one was to have a smaller error rate. Turns out it didn't improve anything. So the pull request was never merged. There is another newer paper, HyperLogLog sketches. There's just a paper, we haven't tried that out in code yet. Maybe this one might improve the error rate, but we are not sure yet. We still need to implement that one. If you're really into the details of that one, read the paper and it will show you how it's trying to improve over regular HyperLogLog or HyperLogLog++, which is the actual implementation that we're using. Okay. Final example, inverse document frequency, which is part of how full-text search works. So before we dive into that, let's see what we have, or let's see the problem. So here we're searching for Luke. This is the query that we've already done in the beginning. I run this, and then you can see we have the first Luke here has a score or relevancy of 3.29. And we would assume that all the Luke documents have the same relevancy because they all contain one single attribute, and that's Luke, and they're all exactly the same. But as I scroll through the list of Lukes here, you can suddenly see this Luke here has suddenly only a relevancy of 0.7. This looks very broken. Like, why is one Luke more important or relevant than another Luke? So let's dive into what is happening here, actually. So let's take a look what is going on here. So the basic approach for scoring is called term frequency inverse document frequency, or TF-IDF. The actual implementation that we're using in Elasticsearch since 5.0 is called BM25, which stands for Best Match 25, which is the 25th iteration of the best match algorithm. Maybe we'll have a higher BM at some point, but right now BM25, or I think BM25F is the current implementation that we have. And what this generally does is it has three main components how to calculate the relevancy. The first one is the term frequency, which is pretty simple. Let's assume you're searching for Luke, and one document contains the term Luke 3 times, and another document contains Luke only once. The document that contains Luke 3 times is probably more relevant for Luke searches than the one that only contains it once. So what this looks like is here you have the number of Lukes, so 5, 10, 15, or 20 occurrences of Lukes. And then how relevant are they? And you can see one occurrence of Luke is less relevant than 3 or 4 or 5 Lukes. The difference between TF-IDF and BM25 is that TF-IDF is just the square root and keeps growing, whereas BM25 assumes that after 5 or 10 occurrences of Luke, there's not much more gain here. So it basically flattens out that curve. It's just tweaking the parameters a bit. But the approach is the same. Like, the more Lukes you have, the more relevant the document will be that contains multiple Lukes. Next up, you have the inverse document frequency, which basically calculates over all the documents that you have, how common is that term, which then means the rare terms are less relevant than the common terms. So if you have something that is rare, it's kind of precious, so the score should be higher, which looks something like this. So here you can see how many times does my term appear? 100 times, 200 times, 400 times, whatever. And then you can see here the relevancy decreases. And this is over all the documents. How many times does Luke appear over all the documents? Maybe, what did we have? 64 times. So it is still pretty relevant. Another example could in Star Wars maybe be father, which will only appear very rarely, but will be very relevant. Whereas other terms might be very common and thus are less relevant. And the final thing is if you have a short field, if your search term appears in there, it's probably more relevant than in a very long field. So this just takes 1 divided by the number of terms, and this is how relevant it is, which is kind of intuitive. If you have a title which has a couple of terms, if Luke appears there, it's probably more relevant than if you have a long description with hundreds or thousands of terms, and Luke appears only in that one. So who can already see the problem of why our relevancy is broken here? Let's see where we can take this. So how do we actually fetch documents or retrieve results in Elasticsearch? And this is where this comes into play. So generally we have 2-step process, query, then fetch. Let's start with the query. So your search request comes into Elasticsearch and you have this coordinating node, which by chance is node 3 here. And that one figures out, okay, you're searching for something in this index, and that index in my example here only has 2 shards. And then it will forward the search request to these shards. Primary or replica shard for a search operation doesn't make any difference. So you can see it forwards the search operation to replica shard 0 and primary shard 1. And then those two will answer to the coordinating node in the query phase, well, I found some documents you have been searching for. For example, if you're searching for the top 10 Luke documents, both shards would say, well, I have 10 Lukes, like here's my list of Lukes. What it actually gives back is the score or relevancy, and the document ID. And if you're searching for 10 documents, each node would give its own top 10 list. And then you have a second phase, the fetch phase, where we actually retrieve the document. In this one here, the coordinating node sends out to the shards, hey, you have the top, first, the second, third, whatever document, and it's only fetching the actual top 10 documents. So we are not, especially if you have many shards, you would otherwise potentially retrieve a lot of data that you don't need. That's why you at first only send the list with the score and the ID of the document that each node holds, and then the coordinating node only fetches the actual relevant documents. And then, in the final step here, it sends back the results. And what you can probably guess, if thinking back about TF, IDF, the term frequency will be the same. Also, the field length is the same. The inverse document frequency, that is the relevant one, because the shards never check like how many looks do you have or how many looks do you have. So based on how many looks are in one shard, some looks might be more valuable than others, because in some shards the looks are very common, and in other shards the looks are very rare. And that's the problem that you have here. How you could fix this is you could add DFS, distributed frequency search, query then fetch. What that basically does is it adds one step before the query then fetch to even out the statistics. So you will have another round trip where the coordinating node will tell the shards, well, tell me how many looks you have. And then for the actual query, it will include and say like, hey, by the way, overall, there are 64 loops. So keep that in mind when you calculate the IDF. You could add that to the query. Let's try that out live. So you have this search type, DFS, query, then fetch. If you run this one, you can see, okay, now my top look has a score of 1.5, and the 10th, because by default you only get 10 results back, still has 1.5. But all the loops would have the same statistic now, or the same score, because we've evened out the statistics. So that was easy. We've done that. Now, the common question that people will ask is, how much performance does this cost? And this is my favorite comic whenever somebody asks about performance. Here you have two similar systems, and you see in one scenario, one is performing much better than the other. And normally it depends very much on the scenario. This is especially what you get when some vendor does some benchmark with a competitor. Like they basically kill the other system by picking the right scenario that is very favorable for themselves, but not the other one. And depending on that, also with DFS, query, then fetch, you could have multiple scenarios. You will definitely have another network round trip, which might be very fast though. Then it will depend, is all the relevant data in memory? Probably it is, so it's potentially rather fast, but there is still additional overhead that you will run into. And the documentation is pretty explicit. You should not really need this. By the way, this is a great URL. You can see relevance is broken. And this is describing exactly the problem that we have covered now. But the base assumption is here that for most scenarios, your data will be evenly distributed. Or turning it in another way is you have normally enough documents that it will just even out. If you have very few documents, you should only have a single shard in the first place, and then the problem will not apply anyway. But if you have a lot of documents, they should in general even out. So you don't really need this attribute. Okay, you might have seen that in 7.0 we changed the defaults of the number of primary shards to 1, because many people had too many shards and there's always an overhead to that. How does that work with our problem now? Also in terms of the FAB theory, what are we doing? Like the big part where we need to parallelize, if we only have a single primary shard, we cannot that easily horizontally scale the write operations then anymore. So we basically trade a bit of the big part for the other parts. Let's see what that actually means. Simon, the tech lead of Elasticsearch, always says, use a single shard until it blows up. And then you know, okay, I have 5 times more data. Then I need probably 5, 6, 7 times as many shards, maybe to have some headroom. But this is the right approach. So for many scenarios, especially for full text search scenarios, you will be fine with a single shard, which can hold, depending on your use case, 10 to 50 gigabytes of data or so. And oftentimes people have way too many shards for the data they have. Like we've seen shards that have just a couple of megabytes, which doesn't make any sense. So just put more data into a single shard. And let's do that now. So what we do here is, first off, we are blocking write operations. So here in my Star Wars index, I block write operations. Once you have done that, I can actually shrink down the number of primary shards. So I take the Star Wars index, I shrink it, and I put the result into a new index called starlet wars. Starlet as in the little star. It's the best name I could come up with. So here we do that. Now we have the same documents in the starlet wars index, but in a single shard. So how does this influence the problems that we've seen? For the full text search or relevancy part, will this influence the result that we get? Yes, no, maybe. Don't say it depends for this one. What you get here is this one will work without the DFS query and fetch, because the IDF is now the same. You have a single shard, so the statistics are all the same. And you can see 1.5 something. If you scroll down to the bottom, it's still 1.5 something. So all of those have the same relevancy. Now, looking at the most common terms for the top one result, will that be influenced by having a single shard? Yes, because every single shard is giving me back the top 11 results. If I have one single shard, the top one result will be in the top 11. So yes, that one is correct as well. And you can see we have an error bound of 0. The cardinality aggregation, is that one being fixed by a single shard? No, that one not, because that is still a probabilistic data structure. If you have a million unique elements, you would still blow up your heap if you would try to create a hash set with a million unique values. So that one is not being fixed. So we've seen those examples. And now you might say that that was kind of a cheap trick, because we've kind of given up a bit of the big to have more correct attributes. So the accuracy has improved, but the big has been kind of like decreased, or it's a different trade-off that we have picked basically here. So to wrap up, it's all about the trade-offs. There is no perfect solution. There is no perfect data store. It always depends. And then you need to think about what does it depend on, or why are the different trade-offs there. We have covered the CAP theorem, consistency, availability, and partition tolerance, as well as our FAB theory, the fast, accurate, and big. And Elasticsearch is always trying to be fast. It's generally trying to be scalable, depending on how many shards you have. We do try to tune the accuracy to give you the other two. But as I've shown you, you could tune a bit the big for some more accuracy depending on your use case. So these are basically the knobs you could turn to get to the results that you want to have. And with that, okay, these are my general slides. I don't have stickers for you today. Find me in person at another conference or meetup, and then you'll get stickers. But let's turn over to the questions. And I think I've already seen there were some questions. So how do we decide how many shards do we need to have for an index which is growing drastically? So generally, the drastically growing index is always something time-based. So you have logs or you have metrics. Previously, we always used, or the default was we use daily indices. So you would figure out how much data do you have per day, and then you basically pick the right number of shards for that per day. But there is now a better approach. Maybe you've seen the rollover API, and with the new index lifecycle management built into Elasticsearch, this is also much easier to run. There, basically, you can define up to 3 definitions of when you want to roll over to a new index. And those are the age of an index, the size, or the number of documents. You probably want to pick maybe a combination of age and size. And you could just say like, okay, once my index has reached a certain size, like let's say 100 gigabytes, and then you use 2 or 3 primary shards maybe for that one. Once it has reached that size, I roll over to another index, and then I have another set of shards there. And that way it is guaranteed that all your shards have the same size. You don't have tiny shards, you don't have huge shards, they're all the same. So that will work out very nicely for you. So if you have some dramatically growing, as you put it, the data set, then probably use the rollover API to make that happen and keep your charts in sync. I hope that answered the question. Second question, can we shrink the number of shards without changing the name of index? No. This is always going to a new index. The pattern that you can apply, though, is you can shrink to a new name, then you delete the old index, and then you use that old name with an alias, and that points to the new name. Generally, especially when you already know you will probably shrink or split up shards, or you will move stuff around, rely more on aliases, because then your application or whatever you're using will never realize that you're changing something in the background. So with an alias, that is possible. By the way, index lifecycle management that I've just mentioned is using the same approach. So you can have a phase where you can reduce the number of primary shards. It will automatically pick a new name. It will remove the old index name, but then it will have an alias pointing from the old index name to the shrunken down index name. So then your application never runs into that problem. Okay, I hope I've answered that one as well. Do we have any other questions? No open questions? Cool, and we're almost up against the hour. Ning, any final words you want to add? Otherwise, I think we're good for today. Do we already have a date for the next virtual meetup? I don't think so.
We just scheduled it. The next virtual meetup will be on 28th of January. So do join us.
Perfect. Thanks a lot. If you have any questions, just find me on Twitter or somewhere online, and I'm happy to answer more of your questions. Thanks a lot. Bye, everyone.